Hi everyone. In this video we're going to write polynomial equations. And if you remember how to write a quadratic equation, a quadratic is a polynomial, and this process is going to work almost identically. Okay, the only difference is instead of having, at most 2x intercepts, you might have a couple more. So we're going to start by writing a polynomial equation with a root or an x-intercept or a 0, whatever you want to call it, at the square root of 3, -4, and then you have a y-intercept. Okay, so when we say a root, that means my x is root 3 and my x is also -4. But keep in mind that this is a double root. We'll get to that in a second. So if I want to write the equation, I kind of want to go backwards and put this in factored form. So normally I'd set it equal to 0 and then solve. Now I got to put it equal to 0 and kind of go backwards from that solving. So I get x minus root 3 equals 0 and x plus 4 equals 0. Okay, so if I'm writing my equation, I'm either writing a function or I've got a y equals some x equation. I know I have x minus root 3, x plus 4. Okay, when it says it's a double root, that means it has a multiplicity of 2, which means the exponent on that x-intercept is 2. It's counted twice. So you could write x plus 4 and then another x plus 4, or instead of that, you can just throw the exponent on to indicate that there are 2 of them. Okay, we're going to take care of that y-intercept in a second, but there's something we need to think about with this root 3. And this kind of goes back to when we talked about polynomial long division. Let's say you're solving for an x-intercept. Pretend it's a quadratic for a second. We could solve for the x-intercepts with the quadratic formula, which is opposite b plus or minus square root, yada, yada, yada. Remember back to the conversation where we talked about, let's say I have a root that winds up being like -1 plus or minus root 3. Then my roots would be -1 plus root 3 and -1 minus root 3. So anytime you have a root, they come in pairs, conjugate pairs with the same root, but opposite signs in the middle. So if I have a root that's root 3, it's really like 0 plus or minus root 3, which is really like positive root 3, and it would also have to have negative root 3. So anytime you see a root that's got a square root left over or an imaginary number, then it's going to come in these conjugate pairs. Now the reason it won't come in a conjugate pair if there is no root or no imaginary number is because then you'd have something like this, -1 plus 3 divided by 2, which is going to simplify to 2 different numbers. So you're going to have -1 plus 3 over 2 and -1 minus 3 over 2, and they're not going to be the exact same number with opposite signs. So in that case, you can't really tell what the other roots are, but if you're talking about a square root or an imaginary number, they're always going to come in conjugate pairs. So long story short, if x equals root 3 is a root, then x equals negative root 3 should also be a root. So setting that equal to 0, you'd have x plus the square root of 3 equals 0. Okay, so you don't need to go through the quadratic formula or think about that every single time. It's just to understand why that would be another solution here. So in my equation, I should add x plus 3, or square root of 3 as well. Okay, so that's my equation. I put it in Desmos. It's going to look like this, which makes sense. It's got 1, 2, 3 x-intercepts, but the end behavior is actually facing up, because if you distribute this all out, you would have 4 x's. So it's an x to the 4th. Anywho, if I find my y-intercept right now, this could take me a second. It's actually down here at -48, but it says that my y-intercept should be at 10. So that means I'm not done writing this polynomial. Okay, the first thing I see people do is they'll add a plus 10 out here. So let's go ahead and try, let's try that again. Let's add a plus 10 and see if that gives me the right y-intercept. Too many plus signs, plus 10. Okay, so here's my graph now. There's my y-intercept. All it's done is shifted it up 10. It's not at 10. So that's not going to work. And the reason that's not going to work is because if I plug in zeros for my x, which my y-intercept is when my x is 0, I'm still going to have this root 3, this 4, and this root 3 plus 10. So So I'm going to multiply these all together and then add 10. And that's definitely not going to stay 10. So if you distribute this all out, that plus 10 is no longer plus 10. Okay, long story short. So what we need to do is, in order to shift the 10 up or down, I need to multiply my y values by some number. Now, first and foremost, my y-intercept is negative right now, but it needs to be positive. So that means this graph is going to need to reflect over the x-axis. And then it's at negative 38, which is too tall, so it's going to need to shrink this graph down vertically. And all that is affected by our a value. So I don't know what number a is, but I can at least put an a there and use this y-intercept to figure out what that a is, because the y-intercept is just an x and a y value. So I can plug in 10 for my y and 0 for my x. And I can solve for that value, which is going to tell me, how much has it been stretched vertically and has it been reflected over the x-axis, so on and so forth. So if I solve for this correctly, hopefully it's a negative number, because that's going to reflect it and make the y-intercept go up here instead of down here. So let's actually do that. Should be doing this on your own. Okay, solve for a. I get, let's see, this is going to be 4 squared, which is actually 16. So I'll have 16. This will be negative root 3 times positive root 3. And if you do negative root 3 times positive root 3, well, root 3 times root 3 is really root 3 squared, so it's going to undo each other, and it's just going to be negative 3. So I will have 16 times negative 3 times a. I'm running out of room, so I'm going to write over here. So I'll have 10 equals negative 48a. Divide both sides by negative 48. It's not going to be pretty, but it's okay. So let's see. I simplify that, divide them both by 2. I get 5 over 24 is my a value. Okay, so I plug that into Desmos. We can just double check that graph. So negative 5 over 24 is my a. And then I have all my zeros, my multiplicity done correctly. Here's my graph, and my y-intercept's where I want it to be. It's at 10. Okay, if you multiply this all out and get it in standard form, you should be able to see that 10. But when it's not in standard form, you will not be able to see the 10. So my final equation is y equals negative 5 over 24. It's not pretty, but it works. X minus root 3, x plus root 3. Oops, I'm running out of room. And then I have x plus 4 squared. And that would be my final polynomial equation. So it's done just like quadratics. Now it's just going to be a little bit more complex. There's going to be higher degrees than quadratics, so higher than 2. So one way you can write a polynomial equation is if you're just given the information. The other you may have to take the information from a graph. So this says write a polynomial equation that could describe the graph below. Now the reason I say could here is because there actually will be able to be more than one answer, because you can't really tell what that y-intercept is. So you won't really be able to get your a value. So let's see how I would do this. I'm going to want to take my zeros, which are right here. So my zeros are at 1, 3. This is negative 1, 2, 3, 4. It's at negative 5. It's kind of hard to see. And then I'm going to want to note the multiplicity. So this one has an odd multiplicity. This one has an odd multiplicity. And this one has an even multiplicity because it bounces. So my polynomial equation could start to look like, let's see, x plus 5, x minus 1, x minus 3. And this could be squared. Now, notice the end behavior here. It's facing, if I continue this forever, it's facing down, down, which means that it got reflected over the x-axis, which means the a value, whatever number it is, would have to be negative. So I don't know if it's negative 1 or negative 2. I'm not really sure because I don't have a y-intercept value to be able to solve for that. So that's why I said write what it could be. If you give more information, you would want to get it more precise, but this is one option. Okay, the other option is it could look like, I don't know, negative 1/2. It could still, or should still have the same zeros, but all I know about these zeros is that they have an even or odd multiplicity. I don't know exactly the degree of the graph. So really, this could be x minus 3 to the 4th. So now let's see, this is the 4th, and then there's 6 x's, so that would still have a parabola-like end behavior. What I mean by that is that the end behavior is facing the same way. Okay, again, I only know that these have an odd multiplicity, so these could technically be 3rd degree, or they could have a multiplicity of 3, because then I would have 3x's here, 3 here, and I'd have 4 here. So that would give me a total of 10 x's, which again would be a down facing multiplicity or end behavior. Sorry. So that's another option for what this graph could look like. Okay, the important thing is that you take the information you're given and you work with whatever intercepts you have, you note the end behavior, and you make your equation match that. So that's how you'd write a polynomial equation. Hopefully this is a good review from talking about quadratics. Please come to class with any questions.